Hi, so I just had a one-on-one session with a student who is having IB exams in less than a week, and we were talking about permutations, and I decided to make a video on the same topic. So permutations is when we are looking at different orders of things. A very familiar example is the card deck, and in fact, just a little digression, I think the most interesting result in the mathematics of permutations, and the most probably deep that I know of, is that in a regular deck of cards, when you have 52 cards, and you shuffle in this way where the cards kind of are supposed to go one after another, like in this picture. It's known that you need at most 7 times to do the shuffling, and once you have done it 7 times, then the order is so chaotic it's absolutely impossible to predict the order of the cards. Now if you do it 1 time or 2 times or 3 times, the entropy, the way we measure chaos in mathematics, is still relatively low, but once you do it 7 times, it's mathematically provable that it's the chaos reaches basically a threshold which is something like 10 to the power minus 10. It's like a very, very small number that or like reaches 1 minus that number. So it's like almost maximal, and then you can't really make it more chaotic by shuffling it any more times. That is, of course, given that you're not a magician who is able to really put them exactly one card after another, because when you shuffle, there's like randomly sometimes 2 cards or 3 cards fall into some place, which makes the randomness, and also assuming that your deck of cards is fair, doesn't contain repetitions, etc., etc. Now, funnily enough, when I was preparing for this video, I realized that my friend made a YouTube video exactly on this topic. Here it is, and I will put a link to the description, where he is a mathematics professor at the University of Helsinki, and he's explaining this random walks on groups idea and how it relates to card decks. Okay, but if you're preparing for IB exams, all you need to know is how to calculate the number of different permutations. So the number of ways you can put things in different order. So here I have an example of 4 different symbols, which are the card suits. And you can put them in actually quite many different orders. So here I have hearts, diamonds, spades, and clubs, but you could have the reverse order, which is clubs, spades, diamonds, hearts, or you could have diamonds, hearts, spades, clubs, etc. And in fact, surprisingly, you have quite many. Let's put all the possibilities here. There are quite many different options. You can have them in different order. And how do I systematically, like I did this list just now, how did I do it? So I first listed all combinations where hearts are first. Okay, so I first listed all possible combinations which start with hearts. Then I listed those that start with the clubs. Then I listed those that start with spades, and then finally those that start with diamonds. And within each of them, I also split them so that within hearts, those that start with diamonds, those that start with clubs and spades, etc. And that repeats. Then we have within clubs we have diamonds, hearts, and spades, etc. And in this way, I can systematically list all of them, and I can make sure that I have actually listed all possible combinations. And so from this picture, you can see that it's easy to compute how many there are. Of course, I could just count, but as you can imagine, if I had 5 or 6 or 10 or 52 symbols or 52 cards, like in a deck of cards, it would be impossible to count, but it is still sometimes possible to calculate. There's a difference between calculating and counting. So since the first, how do we count it? Let's make 4 boxes. So this is the first box, second box, third box, and the fourth box. Now in the first box I put one of the four symbols. As you can see, it's either it's the hearts, clubs, etc. So there are four possibilities what I put in here. Now once I have fixed what is the first symbol, there are three different possibilities what comes next. And so I multiply 4 by 3 because within each of these four symbols we have three categories, and within each category we have two options because the rest can be either this way or this way, but technically the way I'm depicting it here is that the third symbol can be one of two symbols because the other two have been already used up, and the last symbol is only one possibility. So two possibilities for the third symbol and only one possibility for the last symbol because it's always the remaining one. So all possible combinations, the number of all possible combinations is the product of these numbers. So it's going to be 4 times 3 times 2 times 1, which is 24. Okay, that's all fine. So in general, if we have n symbols, then the number of different permutations, the number of different orders in which n symbols can be put is always going to be obtained by multiplying n times n minus 1 times n minus 2, etc. until 1. So multiplying all numbers from 1 to this number. And there is a mathematical notation for this kind of product, and it is factorial. So we're using exclamation mark. So it's going to be n factorial. That's what it's called, and it's denoted like this with an exclamation mark. Okay, let me move myself a bit. Okay, what if I have more symbols? Let's say I have 5 different symbols. Let me just use numbers. So 1, 2, 3, 4, and 5. And suppose that I'm not putting all of them in all possible orders, but I'm putting only part of them. So I'm taking randomly three numbers, and I'm putting those 3 numbers in some order. So I could have 1, 3, 4, or I could have 2, 5, 4, or I could have 3, 4, 1, etc., etc. So now, if n factorial is a way to compute all possible permutations of n symbols, how do I compute the number of all possible ways to take 3 out of 5? In this case, 3 out of 5. The way I take 3 out of 5, I use a similar logic. So I have 3 boxes, and I have to fill them in with numbers from these 1 through 5, and without using any repetition, because I'm always using one number and then it's used up. So the first box can have any out of these 5 numbers. The second box could have any of the remaining 4, and the third box could have any of the remaining 3. So this means that all possible combinations like this, the number of them is 5 times 4 times 3, which is in this case 60. And as you can see, it's the same type of product as this factorial before, but we kind of drop the last bit. So if I had more boxes here, I would continue by putting 2 and 1. So the way we actually get this number is that it is factorial of 5 factorial of 5 divided by the factorial of 2. And in the same way, if I have n symbols or n items and I have to pick m out of them and put them in an order, then the number of all possible combinations of m out of n is going to be n factorial divided by n minus m factorial. And Yeah, and that's it. Okay, so this is in IB. This is denoted by NPM. This number. P stands for permutation. So it's the number of permutations of M symbols drawn out of a pack of N symbols. Okay, suppose now that I'll make myself small. Suppose now that I am drawing cards out of a deck of cards, but I don't care which order they come out. So I don't care about the order, because in the previous example we were drawing like these numbers, like these three numbers out of 5, and but we cared about which order they are coming out in. If I don't care about the order, there are much less different combinations. So we figured out previously that there are 60 different ways to put in an order 3 numbers out of 5. But if I take 3 numbers out of 5 without caring about which order they're in, then I have much less possibilities. I have 1, 2, 3. I have 1, 2, 4. I have 1, 2, 5. I have 1, 3, 4. 1, 3, 5. 1, 4, 5. And then I have 2, 3, 4. 2, 3, 5. 2, 4, 5, and only one more, namely 3, 4, 5. These are the only options in which I can draw 3 numbers out of 5 if I don't care about the exact order. How do we compute the number of these combinations? The way we do it is that we use the previous result. So we first compute all possible combinations of 3 out of 5, but we realize that each of these triples is going to come out 6 times, because, for example, for this 1, 2, 3, we have 6 different ways of ordering it. So we have 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. These are the 6 different possibilities of ordering these 3 numbers in different ways. The same way, we will have 6 times of this one. We have 2, 4, 1, 2, 4, 1, 4, 2, etc., etc. I'm not going to list all of them, but it's going to be 6 of them, 6 of those, and 6 of those. And for the next number, we will also have 6 different ways of permuting it, and for all of these, for each one of them, we will have 6 different permutations. And we computed that all possible ways of drawing out 3 out of 5 is 60. So if this is 60, then dividing by 6, which is this number, I will get the number of these unique combinations, right? Because each combination appears 6 times here, and we get 60 in total. So when I divide this 60 by 6, I get 10, and this is in fact the right answer, because we have 10 of these here. Just let me just check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, perfect. Sorry for drawing again across my head. Oops. Okay. In general, this works completely generally. So if we have n numbers, or n items, n symbols, whatever, and we draw m out of them, this is how I'm used to denote this number, which is by definition the number of ways to pick out unordered sequences of length m out of a sequence of length n. In IB math, typically this notation is used, or sometimes I've seen this notation. So just keep your eyes open. What what you're using, which depends on the textbook, depends on the calculator. The C stands for combinations, whereas P before stood for permutations. Okay. I guess this can also be found to be looking like this. So yeah, there are different notational standards. Okay, and so in general, the way we compute this is, as we just saw, it's the permutations divided by all possible ways of ordering this sequence that we picked out. In this case it was 6. Why 6? Because 6 is 3 times 2 times 1. This is the number of permutations of a sequence of length 3. So this has to be divided by the number of permutations of m symbols, which is m factorial. And so if we recall our previous result, this nominator here is n factorial divided by n minus m factorial, and then when this is divided by m factorial, we can simplify this. Let me just move things a bit. This simplifies to n factorial divided by n minus m. I guess I should use n and k, otherwise they get mixed up when I say them. But here we are, n and m, n divided by n minus m factorial times m factorial. This is the combinations, and here is AAHL official formula booklet of IB, and here we can see that indeed they use this notation version where this first number is uppercase, upper index, and the second number is lower index, and here are the formulas which I just derived. So for combinations you have n factorial divided by r. They use the letter r instead of m. So we have n factorial divided by r factorial times n minus r factorial, and then for permutations we have n factorial divided by n minus r factorial. And good, so we derived these formulas. I think that once you understand how to derive these formulas and you really understand what they mean and how they work, then it's going to be easy for you to solve any exercises where they appear. Obviously, you should still have practice doing the concrete problems and solving concrete questions, but I think any question, any problem involving those should be easy once you understand the basic principles behind this. There are many other interesting things concerning this formula, by the way. It appears in the Pascal triangle. Here we have a Pascal's triangle, and you obtain always the next number by summing up the two previous ones. Let me zoom in a bit. Okay, so you always get the next number by summing up the two previous numbers, and the ones that are directly above it. Let me show it. So 20 is 10 plus 10, 10 is 6 plus 4, 4 is 3.1, 3 plus 1. So you put just ones like this, and then you get all the other numbers you fill in with these sums. And funnily enough, you get, these are actually the binomial coefficients, which are exactly those combination numbers. So for example, this 10 is the one we were just looking at, is selecting 3 out of 5. So it is 1, 2, 3. Well, actually it's 0, 1, 2, 3. So it's the third from the left. So it's this 10, and it's the fifth row. Well, the first one is 0, 1, 2, 3, 4, 5. So the fifth row and the third number from the left, that's the 5 combination 3, so 5 over 3. Yeah, that's an interesting fact that they appear here. You can mathematically prove that, deduce that, and also if you just look at even and uneven, so if you color these by even and odd numbers, you'll get the Sierpinski triangle, which is another cool thing. I'm just gonna show you a picture. This is the Sierpinski triangle. You get this fractal if you just color odd numbers black and even numbers white, or vice versa in the Pascal triangle. You can probably find a lot of YouTube videos about that. So yeah, that's all about combinations and permutations I'm saying in this video. Have a good one and good luck with the exams that are coming up very, very soon.